very happy today to present our latest result on forecasting spintronic experiments using Neural Ordinary Differential Equation, which is a very state-of-the-art machine learning technique. So this talk will be about using machine learning, more precisely deep learning, to predict the result of nanoelectronic experiments. And this work is a joint work between my lab, the lab of the CNRS Thales lab, Beirut University, and Université Catholique de Louvain. And most of the actual results I'm going to present were obtained by our PhD student, Xingchen. But first, let me motivate a little this presentation. The motivation of this presentation is just that nanoelectronics experiments are very hard. I mean, I think everybody who does nanotechnology is aware of this. Materials and device optimizations are very challenging. You need to try many things. And even electrical experiments, when we talk about nanoelectronics, is very challenging. Like you always need to kind of optimize everything, tune everything, find the right condition, and then your device breaks, and you need to do other devices. Always very challenging. And so, for example, if I take this example of our paper that was led by Julie Querlioz, which is quite famous, where we used spin torque oscillators, so a special type of magnetic oscillators, to implement a reservoir computer, and this allowed this, and we showed that this nano device was able to recognize spoken digits. So what is not necessarily highlighted is that each experimental campaign we did on these nano devices took weeks of measurements because the measurements are very slow and there is a lot of optimizing to do. So for this reason, when you do nanoelectronic experiments, modeling is quite critical to be able to predict the result of your experiments and to make your experiments faster. However, modeling nano devices is also very challenging. It's because nano devices tend to rely on very complex microscopic physics that is not easy to model at all. And also because nano devices are so small, you have huge impact of imperfection, non-uniformities, and all the interface effects that have actually very big impact on nano devices and that are very challenging to model. And if I take the particular example of spin electronics, which is going to be the focus of my talk, the gold standard for modeling nano devices is called micromagnetic simulation. So when you do micromagnetic simulation, what you do is that you divide your devices in multiple very tiny micromagnetic cells. And in each of these cells, you solve the differential equations of magnetism. So this is called Landau-Lifshitz-Dilbert equation, and it includes some local and non-local interaction. So just to give an idea, I'm not going to comment that in detail. I wrote this equation here. And you need to solve this equation for all these very tiny microscopic cells. So you can imagine that these micromagnetic simulations, which are actually highly accurate and are really the gold standard in this field, they are also very slow. For example, if you want to simulate a small 122 nanometer disk, including a skyrmion, which is what is represented here. So a skyrmion is a specific type of I'm sorry, of magnetic excitation that is very important in modern research. So simulating this small disk during only 400 nanoseconds takes more than 2 hours of simulation time. Also, although these simulations are highly accurate, it remains difficult to model noise and imperfections in them. So that's why today I'm going to propose an alternative road for modeling nano devices, which is based on deep learning. So deep learning is something that is very important in computer science right now. It is what has allowed all these incredible achievements of artificial intelligence recently. And deep learning is a technique that allows computers to do stuff based on examples. So the idea so deep learning is made by artificial neural networks. So this is a schematic of typical simple artificial neural networks. And the idea of deep learning is that you collect a collection of examples of what you would like artificial neural networks to do. And then deep learning techniques allow you to train your neural network to do what you want. So for example, if I take this very typical example, which is training a neural network to recognize cats, what you do is you would assemble a collection of images. So some of them are cats, some of them are not cats. Then you use all these examples, you use a deep learning technique, and then at the end, your neural network will be able to recognize cats if you present new images, even if they were not in the initial data set, the neural network will be able to tell if it's a cat or not a cat. And these techniques are very powerful. They have been used in many, many fields. And so today, what I'm proposing is to use these deep learning techniques to automatically generate model of nano devices. The idea is going that we are going to just use maybe examples of how the device behaves in some situations, and then the deep learning technique will be able to generate a model able to predict how the device is going to behave in all situations. And for this, we are relying on a very specific formalism, which is called Neural ODE. So Neural ODE is based on conventional ODE, so that's ordinary differential equations, which are very commonly used in physics. So I take a very simple example, which is a spring mass with damping. And it's very easy to write it under the shape of an ODE. So that's the shape of the ODE. The derivative of the state vector y is some function of this vector. So in this case of very simple physics case, the state vector would be the position and the velocity of the object, and the ODE would be given by the physics of the system. And so the derivative of the position is just the velocity, and the derivative of the velocity is given by Newton's law. And that's how typically you write ODEs when you want to model physical system. You rely on the physics. But Neural ODE takes a totally different approach. So Neural ODE has the same shape of the traditional ODE, except that the f function is not given by physics. The f function is actually a neural network. And so, and because it's a neural network, it needs to be trained. So that's why it has all these, we add this theta thing. That means that this S function needs to be trained to do something. And the idea is that we are going to use deep learning technique to train the neural ODE to model a nano device. So for example, if we wanted to train a neural ODE to model this system, what we would do is to assemble sample trajectories of a mass connected with a spring. So this is an example. And then we would use this deep learning technique, and these deep learning techniques would train the neural network in the neural ODE to predict this result. More specifically, for those of you who know deep learning, the technique consists in performing backpropagation over the whole ODE solver, and that's very similar to training a recurrent neural network, because the time aspect in the neural ODE is very reminiscent to the recurrent aspect of a recurrent neural network. And at the end, once your neural network is trained, you get a trained neural ODE, and you can use your trained neural ODE to make prediction on the behavior of the system in any situation. However, when we tried to apply this to spintronics, we encountered some challenges. And the biggest challenge is that when you use neural ODE, you need to know all the important variables. And in this case, it's very easy to identify what are the important variables, which is position and velocity. But when you talk about a nano device, it's much harder. Because, for example, if you look at this nanomagnetic system, you can see, obviously, it has a lot of variables. All these local magnetizations are internal variables. And you can't actually measure all of them. Probably the only thing you can't measure is the average magnetization over the whole device. So you have a very visible variable, which is average magnetization, and then you have internal variables that are important, but that you cannot measure. And normally, if you want to train a neural ODE, you need to know all the variables that are important to show examples to the system. And so that's why in our work, we propose a new technique for this situation. Our technique is really that if you can measure only one variable in your system and you want to train a neural ODE, when you can actually use delayed version of this variable as other variables. Like for example, so if you can measure magnetization, your first variable would be magnetization, but then your second variable would be just the magnetization, but a little shifted in time. And your third variable, it would be the magnetization, just a little more shifted in time. It seems a little counterintuitive, but let's go back to the example I gave. So for example, imagine we can measure the position of our mass, and we don't have the velocity. If we use as the second variable the position shifted in time, you can guess that if you have the position and also the position a little later, it will be very easy for the neural ODE to reconstruct the velocity, which is what is actually important. So in that case, it's very obvious that if you take position and shifted in time position, the system will be able to figure it out. Turns out it's actually a very general result, and in practically all physical systems, this will work. And you can find the demonstration in our paper. So how does it work in practice? So now let's look at an actual example where we apply this technique. So we look at this nanomagnetic device that has a skyrmion in it, and obviously the system has input and output because it's a device. So the input is the anisotropy, which is so this magnetic device where you can actually change the anisotropy by applying voltage to the device. So this anisotropy input is really basically the same thing as changing the voltage on the device. And the other input is the DMI. So that's, I'm not going to be able to say it, but it's a material parameter, which is very important because you can fabricate this device with different materials that will have different DMI parameters. And the output is the mean magnetization of the device, which will translate in the electrical resistance of the device. So you really have a device with inputs K, D, and output M. And it's quite complicated. The physics of this is very complicated, so it can be obtained by micromagnetic simulation. And now we want to find a neural ODE that would be able to model the system very fast. And so what we need is that we need a sample of how the device behaves. And so to generate these examples, we actually use micromagnetic simulation because it's gold standard for modeling these devices. But we use only little of them. So what we did is we generated this training data. So you can see in this training data, we vary the anisotropy of the device, we vary the DMI of the device, and then we did micromagnetic simulation, which is the blue curve here, that tells us how the device behaves when we apply these inputs. And then we train a neural ODE to reproduce that. And you can see this worked. The result of the neural ODE can match exactly what the micromagnetic simulation predicted. So now we have a neural ODE that can model this device. But you can notice that when I did that, I used these very weird inputs that are totally artificial. Because in reality, when you do experiments, you would never apply this type of input. It looks like nothing. Also, the DMI is actually a material parameter. So it does not change in reality. But in the interest of generating a model, we use this totally artificial training set because this way you get with only 50 nanoseconds of data by varying artificially these two inputs. That gives enough information to deep learning to figure out how the device will behave in all cases. And using only these 50 nanoseconds of data that in micromagnetic simulation is very easy to obtain, then the deep learning will be able to generate an equation for the device that works in all cases. And that's the power of the neural ODE. You use very little examples, and then you get a model that works in all cases, and that is very fast to use. So for example, once we have this neural ODE, we can use it to do stuff. So for example, we can simulate our device and plot these kind of curves. Like for example, in that case, that's the frequency of the skyrmion as a function of the anisotropy, or the frequency of the skyrmion, so that's the breathing of the skyrmion as a function of the DMI. So with the neural ODE, we obtain these yellow stars. And we also did the same simulations with micromagnetic simulation, and you can see it matches perfectly. But the difference is that the result of the neural ODE, you obtain them instantaneously, and the result of the micromagnetic simulation, they take hours to obtain. So I only needed 50 nanoseconds of micromagnetic simulation, and then I can get a model that is equivalent to micromagnetic simulation, but that is extremely faster. We also tested this in much more difficult conditions, because this kind of curves is really easy. It's just frequency as a function of input. We wanted to check if the neural ODE still works if you do something very complicated. And an application that is being proposed of our skyrmions is what is called reservoir computer. So reservoir computer, it's a type of AI to some extent that uses the internal dynamics of a device to perform AI tasks. And so skyrmions have been proposed for this. And we wanted to see if neural, so that's very subtle. I mean, it depends on the very much on the details of the dynamics on the device. So if we wanted to see if neural ODE would be able to model that. And so for this application we took is very traditional application of reservoir computing. It allows to predict chaotic time series. So that's very much an example of how you test reservoir computer. It's a task where you have this chaotic time series and you train a nano device to predict what will be the next number in this series. And so we did this. So these kind of things have been proposed already with skyrmions. And we simulated these experiments, and we did it both with the neural ODE, which is the yellow curve, and the micromagnetic simulation, which is the blue curve. And you can see that the two look extremely similar, which suggests that the neural ODE predicts very well the behavior of the device in this situation. But the difference is that the neural ODE was able to simulate these whole reservoir computing experiments in only 20 minutes, while the micromagnetic simulation took 3 days. So you can see huge benefits of having done the neural ODE. And if you look a little more processed result, so here what is plotted is the performance of the skyrmion-based system on predicting chaotic time series. So smaller number is better, and the x-axis is how much in time you predict. Like for example, here you predict the next number, which is easy. Here you predict the number that comes 25 numbers after, which is very hard. And so obviously it's easier for the system to predict the next number. And you can see this result, this prediction, this performance as this kind of counterintuitive shape, which is, and the same shape is found both by the complicated micromagnetic simulation and by the neural ODE, which suggests that the neural ODE really gives equivalent result to the micromagnetic simulations. We also tried that in a more complicated system with 4 skyrmions and some inhomogeneity, and you can see that once again, the neural ODE gives very equivalent results to the micromagnetic simulation. Also now we have a very tiny difference. So here I showed you that neural ODE can learn to predict the results of micromagnetic simulations and then gain equivalent results much faster. You can also use neural ODE to predict directly the result of experiments. And that's what I'm going to show now. And for this, I'm using the results of this paper where we used another type of spintronic device as a reservoir computer. So this time it's not skyrmion, it's actually oscillators that have another type of magnetic structure, which is called vortex, but it's very similar experiment to what I presented with skyrmion, except that in the case of skyrmions, it was computer simulation. Now I'm talking of real experiments with a real device. And I told you before, these experiments are very hard to do. They take weeks. So we wanted to see if we were able to predict the result of these experiments with neural ODE. And what we did is very similar. We took just a tiny piece of experimental results. So that's 5 milliseconds of experimental results. So that's all we use for training the neural ODE. And then we train neural ODE to reproduce this 5 milliseconds of experimental data. And you see this works very well. The neural ODE results match the experimental data perfectly. And here, I told you that our contribution to neural ODE is the fact of having proposed this time-delayed variable. This graph shows that it's actually very important to do that, because if you don't do it, which is the case equal 1, the training does not work very well. Whereas if you add dimension, the more dimension you add, the better the training works, which means that neurology results match experiments better. And then once you have this neurology, you can use it to predict weeks of experimental results. And for example, so this is really the final result where so the goal in that case was to train an oscillator to recognize spoken digits. And what is plotted here is the recognition rate of spoken digits. And what you can see in these blue dots are our experimental results from our 2017 Nature paper. And the light blue curve is what you obtain with the trained neural ODE. And you can see the results are a little optimistic with regards from what we have in the experiments. But that's actually very normal, because the neural ODE is something that is totally deterministic. It doesn't have any noise. And if you look very finely, you will see tiny difference between experiments and neural ODE, which are due to this noise. So but on the other hand, you can add noise in your trained neural ODE. And so what we did is we measured the noise in our training dataset, and we just added this noise to the neural ODE. And when you add this noise to the neural ODE, you can see now the neural ODE results match the experiments very well. So although neural ODE are deterministic equations, you can actually add noise in them and use them to model experimental results that are noisy. I'm sorry. Here you go. Something else I wanted to show is when we use neural ODE to predict other experiments. Because so in these reservoir computing experiments, we can use different types of inputs. So here we use as input what we call spectrogram filters. But in this paper, we also used other inputs that are called Kochler filters, and where the devices are a little different. And here you see something very interesting, is that in that case, the neural ODE with, so you see here, if you use neural ODE without noise, you get recognition rate that is better than experiments, which is kind of expected. Usually when there is no noise, things are better. But if for these other experiments, you can see that the neural ODE without noise gave actually results that are inferior to experiments. And when you add noise to the neural ODE, results become better and match experiments. That was very surprising to us, but it actually, when you look at the details, makes sense. And was a little fascinating that the neural ODE was able to predict this very, very subtle effect that in this very particular situation, noise is actually helpful to the experiments, whereas conventionally, it's really worse, which once again showed us really the power of the neural ODE, and that's why now we want to use it a lot more. So this concludes my talk. So I wanted to show that we propose a technique for modeling dynamic system with multiple inputs and time series output based on examples using state-of-the-art deep learning technique. And it has fantastic time efficiency. I mean, you can train it with little data and the result is very fast. And in the future, we want to explore further, especially the modeling of stochastic effects, because that's the topic where also there was a lot of development in deep learning that can apply it here. So that's all. Here is the reference where you find all this work. And I thank you for your attention.